We're going to take a look at the graded potentials that happen in the postsynaptic neuron. So when the neurotransmitter binds to either the ligand-gated ion channels or the G protein linked receptors that are located on the dendrites or the soma on this postsynaptic neuron here, and we get ions moving in and out of this postsynaptic neuron, we're going to be producing some graded potentials in this postsynaptic neuron. And those graded potentials could either be excitatory or inhibitory. And if they're excitatory, we're going to call them excitatory postsynaptic potentials, or EPSPs. And if they're inhibitory, we're going to call them IPSPs, so inhibitory postsynaptic potentials. So we're just talking about, are we going to be getting close to threshold or not with our graded potentials? And remember, threshold is that magic number, minus 55 millivolts, right here at that axon hillock. And if we reach threshold at the axon hillock, that's going to trigger the opening of the voltage-gated sodium and potassium channels, and that'll trigger an action potential to start, and then we can send that down the axon. Okay, so we've got our EPSPs and IPSPs. So what they're going to be doing, the EPSPs are going to be depolarizing that postsynaptic neuron. So we would have our resting membrane potential here at minus 70 millivolts in that postsynaptic neuron. And if we had an EPSP produced, we would have a depolarizing graded potential. So the membrane potential inside that postsynaptic neuron would get more positive. So we would reach closer to threshold, and that would be excitatory. And if we get a big enough EPSP and we do reach threshold, then we would trigger the action potential to start at the axon hillock. And then an IPSP, what's going to happen there is, if we're at our resting membrane potential of minus 70 millivolts, if an IPSP is created, it will hyperpolarize the cell. So we're going to become more negative inside that postsynaptic neuron, and that's inhibitory because you're getting further away from threshold. You're not going to reach minus 55 millivolts at the axon hillock, and so you're not going to open those voltage-gated sodium and potassium channels, and so you're not going to get an action potential that's going to be triggered. The other way to get an IPSP is if the resting membrane potential is stabilized, and we'll show you how that can happen. So if it just stays at minus 70 millivolts, that just means it's stabilized. So that would also be inhibitory because you're not getting any more positive, you're not getting any closer to threshold either. Okay. All right, so remember that these EPSPs and IPSPs are graded potentials, so they will vary in size. So it depends on how often these presynaptic neurons are firing. So maybe this presynaptic neuron is firing rapidly right in a row. Maybe we have several signals coming down, several action potentials, and we release neurotransmitter, we open up maybe our ligand-gated ion channel, maybe we let some sodium ions in, and then we fire again right away and let some more sodium ions in. And so what happens is we create one EPSP, but before we get rid of that first EPSP, then we let more sodium ions in, and now we add the next graded potential on to what's left of that first one. So if you have this one presynaptic neuron firing rapidly in a row like that, remember that would be temporal summation, right? So you can add these graded potentials together. And so you could reach threshold and then you could trigger, the big action potential to occur. Okay, and that would be starting here at this axon hillock. Okay. So let's take a look at two ways to create EPSPs. So one way is if the neurotransmitter binds to a ligand-gated ion channel, and this ligand-gated ion channel opens, and let's say it's specific for sodium ions. And remember that sodium always wants to enter the cell. So sodium will flow into our postsynaptic neuron here. And if you have lots of sodium coming in, that's going to make the inside of this neuron more positive. So the membrane potential will depolarize, and that's going to create an EPSP. So sodium coming in creates a depolarizing graded potential or an EPSP, right? So that's one way to create an EPSP. The other way to do this is if we have neurotransmitter binding to a G protein linked receptor, and the G protein takes off, binds to an enzyme, we create a second messenger. Sorry, my drawing is a little small here. And the second messenger ends up phosphorylating some proteins. And those phosphorylated proteins will block the potassium leak channels. So remember that leak channels are always open. They're always leaky, okay? And these phosphorylated proteins block them. And remember that potassium always wants to move out of the cell. So sodium always wants to go in, potassium always wants to leave. But if the potassium leak channels are closed, potassium can't leave. It just builds up inside the cell because it can't leak out. And so if potassium stays inside the cell with its positive charge, well, that's going to make the inside of the cell more positive. So that will create a depolarizing graded potential. And that creates another EPSP. So if we close the potassium leak channels, that will create another EPSP. Okay, so I definitely would know these two things. Know what creates an EPSP, because I could have a scenario on the test, say, which of these would create an EPSP, and maybe one of the choices would be, opening up ligand-gated ion channels and sodium coming into the cell. Well, that would be the correct answer, right? Because if you have sodium coming into the cell, that's going to depolarize the inside of the cell and create an EPSP, right? So make sure you know that. Okay, so here's just some pictures from your book showing the neurotransmitter binding to our ligand-gated ion channel. These ligand-gated ion channels that are specific for sodium also do let a little bit of potassium out of the cell as well. Okay, but it's mostly sodium ions that are coming into the cell, and there's just a little bit of potassium that's leaving. So it's the sodium ions that are making the big difference in the membrane potential. So you have lots of sodium coming in, and that's going to depolarize the cell and create an EPSP. Okay, and then here's the other way we can create an EPSP. We've got neurotransmitter binding to our G protein linked receptor, also called a metabotropic receptor. Part of the G protein takes off. We're going to turn on this enzyme. We're going to create our second messenger. We've got cyclic AMP here. We're going to activate our protein kinase, which remember that phosphorylates proteins. And these phosphorylated proteins are going to block the potassium leak channels. So now they're closed. Potassium can no longer leak out of the cell and it just builds up inside the cell. And that will make it more positive inside the cell and create a depolarizing graded potential, or an EPSP. Okay, let's take a look at creating IPSPs. So let's have our presynaptic neuron release some neurotransmitter here. And let's say our ligand-gated ion channel opens, and let's say this one's specific for potassium. And remember that potassium always wants to leave the cell. So if potassium is leaving our postsynaptic neuron here, what's going to happen to our membrane potential? So hopefully you said that the membrane potential is going to hyperpolarize, right? It's going to become more negative. So if you have potassium going out, that's going to create an IPSP. So that's inhibitory because you're getting further away from threshold. You're not going to create an action potential at the axon hillock, right? And then here's another way to create an IPSP is if we have our neurotransmitter release, we bind to this ligand-gated ion channel, we open the gate, and let's say this channel is specific for chloride ions. And chloride ions always do whatever sodium ions are doing. So remember, sodium always wants to go into the cell, chloride ions do the same thing. So chloride ions would move into the cell. And what does that do to the membrane potential? So again, we're going to hyperpolarize it, and that would create another IPSP. Okay. And then there's one other scenario that what if we have both this neuron and this neuron firing at the same time? And so we've opened this ligand-gated ion channel with chloride ions coming in, and then this ligand-gated ion channel, we open this one, but this one lets sodium ions in. So what if we have both sodium and chloride ions coming in at the same time? Well, they'd cancel each other out, wouldn't they? Okay, the charges would cancel each other out. And so your membrane potential would just stay at minus 70 millivolts. So if you have sodium ions and chloride ions coming in at the same time, that creates another IPSP because the membrane potential is just stabilized at minus 70 millivolts. You're not going to get up to threshold. Okay, so that would also be inhibitory as well. Okay, so those are the 3 ways to create an IPSP. All right, so I would know those as well because I could have a question and say, you know, which scenario would create an IPSP? Okay, and if I had a choice where, you know, you were opening up, for example, ligand-gated ion channels that were letting potassium out of the cell, well, that would be the correct answer. Okay, so make sure you know that all of these things would create an IPSP. Okay. All right, and these are just some pictures from your book, just showing you creating these IPSPs. So we've got this neurotransmitter binding to our ligand-gated ion channel that's specific for potassium ions. We open the gate. Potassium always wants to leave the cell, and when it leaves, it takes its positive charge with it, and that will make it more negative inside this postsynaptic neuron and hyperpolarize the cell, and that will create an IPSP. Okay, so this would be a hyperpolarizing graded potential. And then here we've got our neurotransmitter binding to this ligand-gated ion channel. We open the gate and chloride ions come in, and that will make it more negative inside the cell. And we've got this hyperpolarizing graded potential, or IPSP, that we create. And then this last picture, we've got neurotransmitter binding to this ligand-gated ion channel that's going to let chloride ions in. And then we've got another neurotransmitter binding to this ligand-gated ion channel. And so we would have two presynaptic neurons, each releasing their neurotransmitters here. Okay. And maybe this is letting sodium ions in. Okay. And this one's letting the chloride ions in. And so the chloride and the sodium ions would cancel each other out. And so you can see your membrane potential would stay right at minus 70 millivolts. And that would also be considered an IPSP because you're not getting up towards threshold, you're just staying at minus 70 millivolts. So that would be inhibitory as well because they're canceling each other out.